Okay, you see that now. Okay, so the rule says that V and I are constant, right? So we know that, and we know that the datum is at the centroid. So when you see the term that the datum at the centroid, now for this case over here, this geometry, you don't need to use calculation to find the centroid. You can use by observation, right? So through observation, we know if you draw a horizontal line exactly at the center, right? This is our centroid. And why is that? Because the top and the bottom cross-sectional area are the same. Okay, and we know exactly where. And from here, as I said, through observation, you know the distance. You know this distance now. So this distance is 10 plus 30 plus 20. So 20. So this is 60. Okay, it's exactly where the centroid is. Okay, so we know that the datum is at the centroid. Okay, so this is our datum. And the analysis direction is coming down this way. So this is our analysis. Too crowded, pardon me. And we know that this is our analysis direction. Okay. So from here, we can first, we know that given, right, given tau max is equal to 60 times 10 to the power 6 Pascal. Okay. Now, where tau max is, okay, I'm going to write down here where tau max is located. Okay, is located is or tau. Okay, sorry, today. Okay, tau max location is dependent on QZ and thickness magnitude. Okay, I want you to focus on this. Okay, it is dependent on the first moment of area and thickness magnitude. Okay, so we know that Vy over Izz, regardless of the location that we're looking for, this is always constant. Right? Regardless, it is always a constant. Okay. The trick is the tau max is dependent on QZ over T. So what do I mean by that? Okay, that's where this course you require analysis. Okay. The formula is straightforward. Okay, the analysis is not difficult, but it just requires more practice. Okay, so I'm going to copy this image over here. What do I mean by that? Okay, so if we look at the centroid, okay, let's assume. Okay, now we don't know where it is. Okay, I would like to elaborate my point. What do you mean by QZ over T? So now we know that this is our. Again, not working. It's either me or it's the computer now. Oh, it's working now. Okay, so now this is our centroid. Okay, so we know at the centroid, right? Q is equal to Q max, right? Because the area that we have to consider for the first moment of area, it is this area that we have to consider. Maximum area. However, the thickness, right? The thickness is equal to what? 50 millimeters or 0.05 meters. Okay, right? Now there's another location that we need to consider, right? And it's where the thickness is the minimum. Okay, so which location is that? So let's say now, okay, for example, we go look at another location, which is not at the centroid. Okay, the location that we're going to look at is on my blue. I'm going to draw a blue line. Is over here. Okay. So this is not at the centroid. The first moment of area right? So we know that Q, for this case, right? Q is not equal to Q max, right? Because at the centroid is where Q max is. However, T is equal to 0.02 meters. Okay. So it has a lower thickness than at the centroid. So if we go back to that function again, or to that equation, okay, let me, I do apologize. If we go back to the, Eugene, sorry, I got certain, you can see that obsessive compulsive something, probably I have that, okay? I do apologize. So you can see that when we write out the equation, tau, right, is equal to Vy over Izz. And we know this term over here, the top and bottom are constant. Right? Then you have Q over T. Okay. So where tau max will occur have two conditions. So tau max can occur where Q is maximum when thickness is a what? Constant. If your thickness is constant, yeah. Okay. However, tau max can also occur where T is minimum. Okay. So we don't know. Okay? So that's why it's so interesting for this question. We don't know exactly where it will occur. And this is where we have to check. Okay. The thing about this course is this. It's not just knowing, just putting in the formula. It is the analysis. Okay. It is the analysis that makes this course more difficult than other courses. Okay. So now let's start calculating the second moment of area before we go for our break. Okay. So we need to calculate our IZZ. Okay. So determine our IZZ. We know that parallel to the axis, this is our width. And we know that perpendicular, this is our depth. Okay. So IZZ. So I'm going to take so how I'm going to determine the IZZ is I'm going to do the second moment of area for the solid section, and I'm going to minus away the two boxes. Okay, I'm going to minus away the two boxes or the two squares. So the width is equal to 50. The depth is equal to 40 plus 60 plus 20 is equal to 120 cube divided by 12. minus by the two boxes. So the two box, so I need to have a 2 in the front because you have the top hollow square and the bottom hollow square. And then the width and depth is 30 multiplied by 30 cubed divided by 12 minus by the area, which is 30 times 30. And then the distance from the centroid will be 10 down here to here is 20, and this distance is 15. Okay, so it's 20 plus by 15 squared. So this will be equal to 50 times 120 power 3 divided by 12 is 7.2 times 10 to the power 6 minus 30 power of 3 times by 30 divided by 12 minus, oh, not minus, I beg your pardon, it's plus over here. Plus 30 times by 35 squared. Wait, let me do it. 30 power 3 times by 30 divided by 12 plus by 30 squared times by 35 squared, and then times 2 will be 2.34 times 10 to the power 6. So this is equal to 7.2 minus 2.34 is equal to 4.86 times 10 to the power 6 millimeter 4, and this will be equal to 4.86 times 10 to the power minus 6 meter 4. Okay, what I propose is we go for 5 minutes break and then we come back.